It's a special sort of nightmare when you spend hours making videos only to discover that all of them were made without sound. So thank you to Adam who brought this to my attention. And here we go from the top all over again with feeling. So in this video, I wanted to sort of lay out for us a reminder of what we've done so far, and then sort of embark onto our next chapter. So we started by talking about the function basics. I never want us to forget these because they are at the core of everything we say. So what is a function? How do we take a function and make new functions out of it, either by transforming it or by composing it with other functions? And once we built a nice, strong foundation of the basics of functions, we started actually delving into specific types of functions. So our first one was quadratics. It was a pretty easy first moment because most of us have worked with quadratic functions before, but we looked at them more deeply this time. So what did we talk about? We talked about various properties of the graph, right? What do we see about domain and range? What are the intercepts? What properties do we expect these functions to have? So for example, the vertex being either the global max or the global min. The graph has that symmetric quality with the axis of symmetry, a vertical line running through the vertex. And once we had established all of these basics, we can then move on to applications, right? So those were the optimization problems, and it allows us to kind of take advantage of the properties of these functions to be able to answer some pretty interesting questions. The next function on our agenda is a big class of functions known as the exponential functions. So I never want you to forget, going back to the basics, that a function fundamentally works the same way. So you have an input, which we've been calling x, but it doesn't have to be x. And then the function does something to it, and that's the question. What does it do? And it produces an output, right? So we've been calling that output f of x. Graphically, this shows up in the y coordinate, so some people will tell you the output is y. I like to keep it in function notation. So the question is, to call it an exponential function, what is the rule of f? So I'm going to write that here. The rule of an exponential function. So an exponential function is the function a to the x. So that's how this is pronounced. A raised to the power x. So the input is the exponent, right? So that's why it's called an exponential function, is that the input acts as the exponent on the base. A is called the base. And in our definition, the base is a positive number, and not only is it positive, it's greater than 1, okay? So in keeping with kind of the moment that we had with quadratic functions, let's take some time to look at a few examples and establish some ground rules for exponential functions. So I'm going to look at two examples with you all. The first is one that we look at a lot, and you'll see why later. We're going to look at 2 to the x. And then a little bit later, and we'll do this in green, we'll look also at 3 to the x. Okay, so in anticipation of the fact that we're going to look at both 2 to the x and 3 to the x, when we build a table of input-output values, we're going to leave space for 3 to the x. Okay, we're not going to fill it out quite yet, but we're going to leave space for it. In this blank spot that I have to the right, we're going to sketch the graph. Okay. And let's start with 2 to the x. So we'll do that in blue. And for both of these functions, for our inputs, we'll look at -3, -2, -1, 0, 1, 2, and 3. If you want to go beyond that, you can, but I think you'll see very clearly, very quickly, why I'm only using these few values. Okay, so here goes. In blue, let's talk about f. I'm actually going to go ahead and start with the input 1, right? So f of x is 2 to the power x, so the input x as the exponent on 2. 2 to the first is just 2. 2 squared is 2 times 2, so that's 4. 2 cubed is 2 times 2 times 2, which is 8. So what I want you to notice is that every time the input increases by 1, the output doubles. Okay? This is in fact kind of the nature of the exponential function, that whatever the base is, whether it's 2 or 3 or 2.5 or 1.5, every time the input increases by 1, the output gets multiplied by the base. So we'll actually see something very similar with 3. So let's use this to kind of build the rest of the table going up. So 2 to the power 0. Well, some of you might already know what that is, but let's say you either don't remember or you never knew or you're confused by it. Well, whatever 2 to the 0 is, when you double it, you get 2. So say it with me. What would you double to get 2? Well, 1, of course. Same thing for 2 to the negative first power. Again, so some of you might remember this from like your past lives or your work with exponents in the past. You've all probably seen this before. But if you're confused by it or you don't remember it, 2 to the negative first is whatever you would double to get 1. Well, what would you double to get 1? A half. 2 to the negative second is whatever you would double to get a half. So what would you double and get a half? Well, a quarter, of course. And then last but not least, 2 to the negative third is whatever you would double to get a quarter, and that's an eighth. Okay, so I'm going to make a quick summary statement about this later. So we're going to make a little box down here at the bottom. So a few tidbits about exponents that we'll kind of revisit after we're done with talking about G also. So we'll leave a little space for this here. All right, well, let's go ahead and plot the graph. So 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. Then we have 8. And if you wanted, you could keep going, right? So I don't have it in my table, but 2 to the 4th power, you would double again. So that would be 16. And that's like up here. It's above, it's kind of up there somewhere. It's above what I've made space for in my graph. So we'll agree that there's a very steep incline and it goes off the chart for this. In the other direction, so at -1, we're at a half. -2, we're at a quarter. And now I think you guys can see why I stopped it at -3. Because very quickly it becomes hard to graph well because the numbers are so small. But notice that every single time I go over one more to the left, I'm just taking half of the output that came before it. So no matter how small the output, it's just going to keep getting smaller, but it's never going to get to 0, right? It'll get so small that we might not be able to see it very clearly on a graph, but it's definitely still there. So what's important here is that the outputs are going to approach 0. They're going to keep getting smaller and smaller. They're going to tend towards 0, but they're never going to actually get to 0. So we'll think about what that means from a function perspective in a second. So here is the graph. And again, so this is kind of tending downward like so, without ever quite getting there. All right, good. So that's the graph of 2 to the x. In a second, we'll talk about domain and range, but we'll work on 3 to the x first. So let's see with 3 to the x. I'm going to start exactly the same way. So 3 to the first power is 3. 3 squared is 9. 3 cubed is 3 times 3 times 3 is 27. And I want you to notice again that for every time that the input increases by 1, the output gets tripled. So just like we had with 2 to the x, where every time the input increases by 1, we multiply by the base. Same thing here, just this time the base is 3. Okay, so let's work our way backwards to figure out the rest of the outputs here. So 3 to the first power is whatever you would triple to get 3. Well, what would you triple to get 3? Well, 1, of course. Same thing. 3 to the negative first power is what you would triple to get 1, which is 1/3. 3 to the negative second power is whatever you would triple to get 1/3, which is 1/9. And lastly, 3 to the negative third power is whatever you would triple to get 1/9. So you can almost think of it as like working backwards. You're dividing by 3 each time. So let's plot this on the graph. Notice this graph also goes through 0, 1. It goes through 1, 3. It goes through 2, 9. And then 3, that's all the way up at 27. So that's way off the charts, right? Like that's up there somewhere. It's definitely off of the scope of our graph. So we see that the growth between the inputs 2 and 3 is very, very steep. So we'll sort of be mindful of that, and we'll be okay not plotting the point at 3. In the other direction, exactly the same thing, but kind of in the opposite way. So at -1, we're at 1/3. Then we're at 1/9. So again, these values on the negative side get very small very quickly, but still, even though they're very small, each next one, we just cut the previous one into 1/3. So we never get to 0, we just have a very, very, very kind of rapid approach towards 0, but we never get there. So there is the graph of 3 to the x, and you see that shape-wise, it's a very similar shape to the graph of 2 to the x, but more exaggerated. It's steeper. The incline is steeper on the right, the decline is steeper on the left. But all of the properties and all of the main ideas are the same, which is why I held off on talking about the domain and the range until we had both of them on the page. So when you're looking at the function, it becomes clear that even if we don't quite remember how properties of exponents work, and we will review them as we need them, it's clear that the exponent can be any real number. It's clear that this graph goes on forever and there are no jumps in it. It goes on forever in both directions, so the domain is all real numbers. So the domain is all real numbers. And this is actually something that we're going to notice about all exponential functions, and we'll see it a little bit more in our next video. The only way that you can encounter a function that's exponential that doesn't have a all real number domain is if it's been composed with a function whose domain is not all real numbers. So you can manufacture an exponential function without an all real number domain, but you have to use composition to do it. Left up to its own devices, an exponential function will not have domain issues. Now let's look at the range. So remember how we said that as we're looking at the negative side, this left-hand side, the graph approaches 0, both the green and the blue, but it never actually gets there. So the range is all positive numbers, or in interval notation, from 0 to infinity, not including the 0. The thing that maybe you all were thinking as I was describing what was happening there on the left-hand side is, wait a minute, this is asymptotic. And you would be absolutely right if that's what you were thinking. We keep approaching 0 without ever getting there. That is an asymptotic trend. And so, in fact, the exponential function a to the x is going to have an asymptote, y equals 0. So let me just kind of summarize what I said over to the left here, and I'll do it in a second. But what we're seeing here with the domain, the range, and the asymptote, that's actually true for all exponential functions of the form a to the x. Okay, so I'm going to spend the last few moments of this video summarizing a few things. So number one, few tidbits about exponents. A to the power 0 is equal to 1. I should say here, unless a is 0. And I'm going to put dot, 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 because for our purposes, that's not something we worry about too much, since for our purposes, a is defined to be a number greater than 1. However, it is something to sort of be aware of, because you may come across a situation where the base is allowed to be less than 1, and then you have to be careful about 0 to the power 0 because that's undefined. If you don't remember why, or you're curious about why, feel free to ask. The other thing that I want you to notice, and you can see it here in the tables that we built, if you compare powers that are opposites, so 2 to the third and 2 to the negative third, 2 to the third is 8, 2 to the negative third is 1/8. 3 squared is 9, 3 to the negative second is 1/9. So what we start to see is that negative exponents cause a reciprocal. So a negative power is simply a reciprocal of its positive counterpart. So this is going to be something really handy for us to remember for later, that all that a negative exponent causes is it causes a reciprocal to happen. Again, to see why, just look at what we did here with the observation that for every time the exponent increases by 1, the value just gets multiplied by the base. So that idea is really instrumental in understanding why there's this business with the negative exponent. All right, so the last thing I want to do in this video is kind of a summary of properties for the basic function. I'm going to put a few things. So number one, the domain is all real numbers. We are not going to encounter in this class any exponential functions whose domain is not all real numbers. The range of the basic exponential function f of x equals a to the x consists of strictly the positive numbers from 0 to infinity. The basic exponential function f of x equals a to the x has an asymptote. And that's y equals 0, meaning that the graph approaches 0 without ever getting there. And then a few kind of small things. So the graph of this function passes through the point 0, 1. If you were to graph a bunch of bases, and I think you have a problem in your homework that kind of does this, if you were to graph many, many bases in all different colors, you'd see this bouquet of function graphs, all of which pass through this 0.01. So it's kind of cool to see. Of course, when you do it by hand, it gets very claustrophobic very quickly, but it's a nice picture to have a computer generate. So the graph will pass through 0, 1. And then lastly, the shape of the graph. And I think that at this point, you guys have kind of learned that I'm all about shape. The shape of the graph is something like this. You'll hear me sometimes call it this weird J-like shape, but you have a very steep side on one side, very rapid incline on one side, and a very gradual decline towards 0 on the other side. This is mostly everything that I wanted to say to you. I will leave you with one last kind of like thing to think about or thing to notice. And this feeds into something that we've been talking about, which is the exponential function a to the x appears to be 1-to-1. Right, so I'm hoping that from our previous lessons, you remember what that means. I'm hoping that you're looking at it and you're like, oh yeah, totally. And I'm also hoping that when I say that, you kind of see why I would care about it. But we will say a lot more about it in the coming videos. All right, so this is our first video of the week. Next one coming up soon.